Hello and welcome to lesson 13. Now, in the previous lesson, we examined the Giesecke's constitutive equation and found that, amongst other things, it predicts a non-zero first and second normal stress difference. We've mentioned normal stress differences in passing a number of times now, so the time has come to examine these material parameters more formally. Many rheology courses introduce the concept of normal stress coefficients alongside the concept of viscosity, as all three of these quantities describe the deformation response of a material. I've left discussing normal stress properties until now, however, since up until recently we haven't come across a situation where normal stress differences would be non-zero. As we will see, normal stress differences are responsible for the unusual flow effects that we observe in viscoelastic materials. So let's firstly examine what these differences actually are. So here on my blackboard, I'm going to put a diagram of a flow. Now, to start with, I'm not going to put any coordinate directions on this flow. I'm going to acknowledge there's a flow direction and there's a direction in which that flow velocity changes. So let's just stick with that for now. And what we're going to say is my flow direction is direction 1. And the stress, the principal stress in direction 1, tau 1,1, is the normal stress along the streamlines. These streamlines could be going in the x direction, the theta direction, the phi direction. It doesn't matter. Tau 1,1 is the normal stress along the streamlines. We're going to define a direction 2, and that is the flow gradient direction. So tau 2,2, therefore, is the normal stress in the direction of the flow gradient. That's going to be perpendicular to the streamlines in one of the planes. And again, this could be in the theta direction, the z direction, the phi direction, the x direction, depending on our coordinate system and depending on our flow. However, tau 1,1 is always the normal stress along the streamlines, whichever direction they're going in, and tau 2,2 is always the normal stress in the direction of the flow gradient. There is, of course, a third direction, and that is a direction that is mutually perpendicular to both of these directions. In our particular case, it is going into the blackboard. I'm going to call it a transverse direction, and this is direction 3, and consequently tau 3,3 is the normal stress in this transverse plane. So, now that we've thought about that, let's think about differences in these stresses. I'm going to define my first normal stress difference, N1, as the difference between tau 1,1 and tau 2,2. So the difference between the stress that you find along the streamlines versus the stress you find in the flow gradient direction. The second normal stress difference, therefore, is tau 2,2 minus tau 3,3, the stress that you'll find in the flow gradient direction, less the stress that you're going to find in that transverse direction. So those are the key definitions of our first and second normal stress difference. They're coordinate independent because the definition depends on the direction in which the flow is going. The 1,1 direction is representative of the stress along the streamlines. The tau 2,2 direction is representative of the stress in a direction perpendicular to the streamlines where there's a flow gradient. And tau 3,3 is perpendicular to both of these directions. So let's put this in terms of a more concrete example. Let's say I have pipe flow, and there on my board I've got a sketch of a velocity gradient within a pipe. Now I'm going to define some axis direction. So my flow here is along the axis of the pipe in the z direction. My flow gradient is in the radial direction, and we can see that in the central line of the pipe I have my maximum flow velocity. And at the walls of the pipe, I have zero flow velocity due to that no-slip boundary condition and there being stationary walls. The theta direction is going to be in a rotational direction around that z-axis, and that's my transverse plane. So for this particular example, my first normal stress difference, N11, is going to be tau 1,1 minus tau 2,2. Now tau 1,1, the direction of the flow, is going to be tau ZZ. Tau 2,2, that gradient direction, is going to be tau RR. So N1 for this pipe flow is tau ZZ minus tau RR. N2, therefore, is tau RR minus tau theta theta. So that's how I would write the first and second normal stress differences for pipe flow given this coordinate system of flow geometry. let's look at another example. Let's say I've got couette flow. So we have a cylindrical bob in a container that is also cylindrical, full of fluid, and we're rotating that cylindrical bob in a stationary container. Again, let's put some axis directions on this. My z-axis describes the length of the couette up and down in this diagram. The radial direction is simply the radial direction out from that axis of rotation. And the theta direction is actually now the direction in which that bob is turning. So, N1 in this case would be defined as my streamline direction, which is now my rotational direction, less my gradient direction, so that's tau theta theta minus tau RR. And N2, therefore, is going to be tau RR minus tau ZZ. So there we have two examples of how to apply the concept of first and second normal stress differences to two examples of flow in cylindrical coordinates. Now, we said at the beginning that normal stress differences are responsible for most, if not all, of the unusual flow phenomena that we see with viscoelastic liquids. So let's spend a little time thinking now about some of the manifestations that happen in normal stress differences. Again, let's consider pipe flow, and let's consider what these normal stress differences actually mean for the fluid flowing in this pipe. My flow direction is along the axis of the pipe in the z direction, and my flow gradient direction is radial. So, my first normal stress difference, therefore, is tau zz, my flow direction, minus tau rr, my gradient direction. And if I sketch this out on an elemental body of fluid, which will be cylindrical in this coordinate system, tau zz are principal stresses acting like so, effectively pulling this cylindrical element. Tau rr is going to be acting so, in a direction that is perpendicular to tau zz. And so if we think about that little mental model, if my first normal stress difference is greater than 0, that implies that tau zz is greater than tau rr, and my first normal stress difference manifests as tension in my streamlines. And there's a really nice visual way that this can be seen. If you get a very viscoelastic fluid that's got a relatively high flow viscosity and pour it from a beaker and then cut the fluid, you can see something quite interesting happening. So I found some pictures of this for you. In this first picture, you can see that there's a conical flask of highly viscous, viscoelastic fluid being poured into a beaker. And there's someone standing there with a pair of scissors. And what they're going to do is they're going to cut that flow in half. And so this second frame shows that flow being cut in half, and you can see it's ruptured. And then, rather beautifully, in this third frame, what you can see is the upper part of the flow that's been cut, the part that's coming from the conical flask, has retracted back into that conical flask. It's almost as if what's happened here, you've got a piece of elastic, for example a bungee cord, that's under tension, and it's been cut, and it's relaxed back, and it's pulled itself apart. That's exactly what's happened in this fluid. And this is a very, very good visual prompt for what tension along streamlines looks like. And that is down to our first normal stress difference, N1. Let's think about a second flow manifestation. And this is going to become really relevant when we think of both rheometry, how we measure these normal stress differences, and also some of the flow effects that we see in practicality. And this was a really, really nice experiment that was reported in Rheologica Acta some years ago now, and it was reported in German. And they described something called the Quelleffekt. What we have here is a cylindrical vat of fluid, much like you find on the outer part of a couette cell. Rather than put a couette bob in there, what we're going to do is place a turntable in the base of this. So we've got a rotational plate. I've put some coordinate axes on here, so my axial direction, my z direction, is up and down, my radial direction is out from that center of rotation, and my rotation direction is the theta direction. So if we think about this in terms of how the flow is going, the flow is going to be going in that theta direction, in that angular direction. So that's going to give me my streamline direction. And the streamlines are going to be going round and round and round, but the flow gradient is in the radial direction because we've got stationary walls. So if we think about what this means for N1, our first normal stress difference, it's tau theta theta minus tau RR. Now, when this plate is rotated, rather than seeing the fluid dip in the middle, as you might expect for a Newtonian fluid as that vortex forms, what you see is a lump appear in the middle, as fluid sort of bunches together into the middle and starts to try and go upwards. We can think about why this is happening if we look at this in plan view. So here we've got the plan view of this cylinder of fluid, and I've sketched on the streamlines here. Now, we said that the first normal stress difference can be visualized as streamlines under tension. So imagine what we've got here are a series of things under tension, a bit like surface tension in a way, squeezing in. And as much as when you have surface tension on a bubble, it creates a Laplace pressure inside that bubble, which means that the pressure inside the bubble is higher than the surroundings, and the higher it is depends on the radius of curvature of the bubble. What we have here is tension in the streamlines effectively trying to strangulate this liquid. And the net effect is it migrates to the centre of this flow geometry. And so if we think about this, our theta direction stress is going to be angular like so. My radial direction stress is angular like so. And what we have is what's termed the flow strangulation effect. And if we look at tau theta minus tau RR, that is my first normal stress difference, N1. It's actually a little more complicated than this, as we'll see in other parts of this lesson. But in terms of a mental model, it's a really good one to visualize why, rather than getting a dip in the middle of this geometry, you actually get a bulge. So let's briefly sum up some key points. We've been talking about first and second normal stress differences, and the first thing we need to do is to make sure we've got our definitions right. So tau 11 is always the normal stress in the flow direction along the streamlines. Tau 22 is always the normal stress in the direction of the flow gradient, and tau 33 is the normal stress in a direction that is mutually perpendicular to both tau 11 and tau 22, and I've called this the transverse direction. So the first normal stress difference is tau 11 minus tau 22, and we've seen various examples of this now in different coordinate systems of flow geometries. And our mental model is to think of this as tension in streamlines if our first normal stress difference is greater than 0, i.e. when the flow direction stress is greater than the flow gradient direction stress. Our second normal stress difference, tau 22 minus tau 33, can actually be thought of as long as compression along the vortex lines if N2 is less than 0, but we're going to explore this in more depth in future parts of this lesson.